Welcome to my presentation of our work towards faster reasoners by using transparent huge pages, which is done by Johannes, Fichte, Norbert, Manthey, which is myself, Julian, Stecklina, and Schidler. I briefly give a motivation and a very brief summary. So, as a motivation, there's many tasks of automated reasoning, for example, verification of hardware or software, anytime optimization problems, which give a better result the longer you let them run, and time-bound nightly jobs like analysis or verification, where in a given amount of time we try to squeeze in as much computation as possible. The question behind this work was, is there a way to improve all of these in an easy to consume way? Because there's already solutions, so as a related work, you can improve algorithms or data structures of solvers or automated reasoning tools, which give a high benefit at the cost of high analysis, research and implementation costs. And then there's one-time improvements. There, for example, is improving the memory layout, which requires to change a few lines. There is prefetching memory by adding a few instructions, which is typically 1 or 2 lines. Or in this work, we present to use huge pages, which basically requires you to recompile your tool once. And that's relevant for most of the distros, except, for example, Red Hat Enterprise Linux 7, because they enable huge pages by default for the whole system. So, a very brief summary is, if you use huge pages instead of small pages, then you get a speed up of an average 10%. Depending on the benchmark, it can be much higher. And this is a summary of how you achieve this. So, the first box shows you how to check whether your system supports it. The first command should give you a result always or advice. The second line shows you how to monitor whether you actually use huge pages and how many pages are actually used at the moment. The second block shows you how to do this with administrator privileges, so you can install a package to easily modify the system settings to use the overall system settings for your tool as well as all the other systems that are running on your machine. Or, and this is the contribution of this work, you recompile your tool statically once. And there's a Docker file from the MiniSat repository which you can use to do that. So you use the command with your build command and then tell it to statically link against the modified glibc that comes from this Docker container, which for each allocation tells the kernel to use huge pages if possible. And then finally you can invoke your tool with the environment parameter glibc thb always equals to 1, and it will use transparent huge pages. We would love to hear about your experience with this and whether you get the same speed up for tools of your domain. For the more detailed version, and I want to give some preliminaries, afterwards talk about how huge pages are useful to SAT solving, present some results, and finally conclude. So first, what is SAT solving in a nutshell? It's an NP-complete task where, given a conjunction of clauses, one should find a satisfying assignment for all the variables if possible, or return a proof that it's not possible. And for industrial problems today, there's millions of Boolean variables and clauses. Techniques that are used by today's SAT solvers are the two-watch literal unit propagation, data structure, and algorithm, which consume 80 to 90% of the solver's runtime and make these large formulas and good solution times actually possible. They nowadays treat binary clauses specially. SAT solvers, from an algorithmic point of view, do conflict analysis, add learned clauses, perform backjumping instead of backtracking, and also remove learned clauses again. They restart search, they have heuristics on how to search and where to search next, which depend on the recent search state, and they also have formula simplifications and many more small things that make them very efficient tools. So if you look into the memory consumption of a known solver, namely MiniSat, on a benchmark that covers many areas of industrial problems, then you can see that half of that benchmark requires MiniSat to consume more than 100 megabytes of main memory, and having a CPU architecture in mind, then that's quite a high number. The second half of the benchmark requires the tool to consume between 100 megabytes and 4 gigabytes of memory. So from an architecture point of view, the interesting piece here is the memory subsystem, where memory accesses use virtual memory from a programmer's point of view, and then the CPU and hardware actually needs physical addresses to access data. So we need to translate from virtual to physical addresses, which is implemented by a page table walk for several pieces of the address, and that is up to 5 table lookups in recent CPUs. And to not rerun the same translation each time, the translations are done on page granularity, which is typically 4000 bytes for usual pages, and then there's a cache which is called the TLB that caches translations, so recent translations can just be looked up. From a size point of view, there's the CPU and registers, then there's L1 data and instruction caches with around 64 kilobytes, then there's an L2 cache which has half a megabyte usually, and some CPUs nowadays also have a last level cache, which is level 3 cache here with about 4 megabytes. And then there is a TLB, also in several levels, which is entries for 4K pages or for the larger, huge pages for 2 megabyte pages. And the level 2 TLB has 1500 entries, which can cover 6 megabytes for the 4K pages, or it can cover 3 gigabytes of cached translations. And this is the major difference this work is going to target. And then there's main memory, which is more than 4 gigabytes nowadays, given that memory is pretty cheap. Okay, now how does the TLB work and help our translations? So basically there's a virtual address used in a program, then there's a TLB and there's a lookup, and if there's a hit, then you just get the physical address back and then you can exit the data from there. Or there's a TLB miss and then you go into the page tables and you do your 4 to 5 lookups, and if you have the translation done, then you return the virtual address added to the TLB and then get the physical address to use with it and continue. So why is huge pages relevant for SAT solving? So as I said earlier, unit propagation takes 80 to 90% of the runtime. So how does that actually work? So there's a list of literals to propagate, because from the current partial assignment, those literals have to be assigned to true to not result in a conflict. So we run the following until closure or until conflict. So it picks the next literal of the sets of literals to propagate in a depth first search order. Then there is an occurrence list called LP of clauses that have the negated literal of the one that we just want to propagate. And then for each of these clauses in this list, we check whether the current assignment falsifies the clause or whether it turns it into unit, or whether there is another literal that is not assigned yet which could satisfy the clause, so that we have to move it from the current list into another list, so that when we propagate this other literal, we have to check that clause again. Now, when we analyze how many TLB misses are done in this algorithm, we can see the following thing. So as expected, the lines B3 and B4 are hard to predict. They benefit from prefetching already, so this is a prior work. And 80% of the TLB misses also happen here, so accessing the next list of clauses that have to be propagated contributes 80% of the overall TLB misses. And now, surprisingly, line B7 gives the next big blob of misses, namely 10% of TLB misses. And again, it's hard to predict where that access actually goes to, because we don't know in advance which literal to watch next from a clause. We only know that this has to be one that is not assigned yet. Okay, so what can we do to apply huge pages? So there's different alternatives. One could actively use huge pages by telling the system in advance that one wants to have it, and then one can pre-register a given amount. Then the kernels support using huge pages transparently, so one could just apply that system-wide as presented earlier. And then there's other alternatives if you don't want to change the system setting but only want to tackle a single program. Then you could modify the tool source code, which would work for a single tool, but which would have to be ported to different tools. malloc could be modified, so whenever you allocate something with the malloc function, you also go to the kernel and say you want to have huge pages. That also doesn't work, because typically you allocate small chunks, especially for the watch lists, which is the part that contributes most of the TLBs. They are much smaller than 2 megabytes, resulting in the system not giving you a huge page, but actually only providing small pages. And then the final approach that is taken in this work is to modify glibc so that below malloc, the functions that are used actually always ask the kernel for at least 2 megabytes or multiple thereof, and then use the madvice system call to say the given allocated memory blob should be allocated as a transparent huge page. So if possible, the kernel should use a single huge page instead of splitting these 2 megabytes into multiple 4K pages. The patch is about 500 lines and it's in the upstreaming process, so it hopefully hits the upstream glibc and then is also available in many distributions. You could try it yourself, as explained earlier, basically by recompiling your tool in a special environment with a modified glibc, and then you can enable the change with an environment variable. We already provide a few compilation instructions and also provide the way how to run the tool. So results, we did some measurements. Basically, we took MiniSat on the same benchmark again, and we modified it with using transparent huge pages, and you can see the benefit here. So this is a cactus plot, which means if the tool is more right, then it's better. And now one could say it's hard to read, so we did the same measurement, so it's the same benchmark and the same data points, so just a different representation. So on the x-axis, you can see the time of MiniSat with the change enabled, and on the y-axis, you can see the time that is used by the tool without the change enabled. And you can clearly see that most of the data points are above the identity line, which means the tool is faster. Now one could claim MiniSat is an old solver which hasn't been changed recently, and the modification is not relevant to modern systems. So we add one more tool to this, which is Catechol, a sophisticated SAT solver that has won competitions recently and that already takes care of improved data structures and algorithms. And you can see that the dots that are representing benchmarks that have been run with Catechol also are placed above the identity line. Now in this plot it's hard to read what's the actual speed up, so we can add more lines to this. Now there is 2 more lines, again the identity line, which is the lowest one, and then one line representing 10% speed up and another line representing 20% speed up. And you can see that even for formulas and the Catechol solver, there is speedups of more than 20%, as nicely seen in the middle of the diagram. Okay, so in a more comprehensive way, we did this change measurement for different tools and different categories. So for plain SAT solvers as MiniSat or MergeSat, you can see that the average improvement is about 13%. And for related domains like ASP solving, for example, the average improvement we measured is still 10%. For optimization problems, for example, by using the Open VBO tool, we still get 8%. And for extracting unsatisfiable cores from formulas, similarly, calling SAT solvers multiple times, you at least still get 5% of improvement in average. For verification tasks, so for hardware model checking and software model checking using BMC tools, so CBMC for software and IBMC for hardware, you get 4 or 2% or almost 3% speed up. Now what can be seen is that with a plain single call to SAT solver, you get a high amount of speed up. For tools that use SAT solvers but also run other algorithms, the speed up is not that high because these tools also spend time in different parts of the algorithm. And we also showed in a public competition in the 2019 hardware model checking competition that if you use huge pages instead of small pages, you can get up a speed of about 5%. Now future work, so at the moment we only presented results for bare metal machines, so tools running actually on your CPU. For VMs we expect higher gain, so because there's more address translations involved, we expect that these translations are cached more, meaning there's more speed up, and because there's more translations there should be a higher impact. Furthermore, all the measurements have been done on Int'l CPUs at the moment, but there's also other manufacturers, so we plan to measure the effect on AMD and ARM CPUs, and we expect similar results because the basic architecture is the same. And we also mainly measured SAT-based systems and then ASP, some optimization, and BMC tools. We should broaden this to more categories, so we will look into SMT more, and for tools that have similar watch list or occurrence list data structures, we expect the speed up to be similar to what we measured for SAT systems. So this concludes the talk. If you can choose, you should use transparent huge pages because it gives you a speed up of about 10% compared to what you have at the moment. This work showed the effect of actually doing so for SAT solvers and related tools. And furthermore, we made using huge pages easily accessible. It only requires compiling your tool one more time in a Docker environment with a modified glibc. So what do we do to plan next? We want to upstream the changes. We want to bring huge pages into other domains and check the effect there, especially for algorithms that are depth first search like SAT solvers. And we also want to investigate other architectures, containers, and the effect in VMs. Thanks for listening. This final thanks slide gives a pointer to our repository that gives many compilation instructions for tools that then can use transparent huge pages, and there is another link to the actual patches in case you're interested. Thank you.